yesterday, showing you how we build these product programs to prove relations among cryptographic games. I presented it to you with some kind of hesitation, in that I knew it sort of has its warts. There were some, for instance, Fritz and others which were saying, well, wouldn't it be nicer to be able to specify these relations among programs as things like logical relations, these kinds of things. And my remark then was, yes, that would be nice, but we don't quite know how to get it to scale to the level of complexity of the protocols that we're interested in. So what I'm going to do today is to show you how the path we're kind of taking to try to get relational reasoning in the style that I think we might all like a little bit better, that's a bit more reasoning about relations among the denotations of programs, rather than building these kind of product constructions. And we're going to see how far we can get with this. And we can get reasonably far, and it's not, but we don't quite get as far as we'd like to get, or the examples I showed you yesterday. And so maybe at the end of this lecture you can kind of see a path of a research agenda, how to scale the stuff I'm going to show you today, the stuff I showed you yesterday. So what's relational verification? So it's broadly, I see it as relating multiple programs, or relating multiple executions of a single program. And there are many examples of properties that you might want to verify in this manner. There's things like program equivalence, correctness of program optimizations, for instance. There's program refinement, for instance. You could start with a high-level program and successively refine it to lower-level implementations, each time proving a relation between adjacent programs. There's security properties. Things like non-interference are inherently stated as properties, as relations among pairs of traces in programs. So there's a wide variety of these things. And this first part of the talk is based on a paper that we had last year at CPP, and it's about a framework for relational verification in F star, and it's a monadic framework. One thing to observe is that if you have pure programs, stating relations among pure programs is kind of easy. It's just talking about two functions and saying, relating their results and so on. And we know how to do that pretty well. Many proof of systems have support for stating relations among pure programs. One of the main difficulties is how do you state relations between effective programs? Well, let alone do proofs, how do you even state the relations in some sense? And there are many custom logics and tools out there that support stating and proving relations among effective programs. There's a paper by Nick Benton, there's a Powell 2003 or 2004 paper. It's a very nice paper. And it sort of, I think, kicked off a line of research on doing proofs using relational Hoare logic, where it's a Hoare logic which relates pairs of commands by a relational pre and a relational post condition. And there's been many systems following it that add more sophistication. For instance, the work by Gilles Bart's group looks at how to add probabilities into this picture and do probabilistic relational Hoare logic. And there are tools based on it. There's a tool called EasyCrypt that does cryptographic proofs. Probabilistic equivalence is about cryptographic programs. There are many others. Type systems for information flow control are a good example of this, where it's a system, in a way, a program logic or a type system that's geared towards proving one particular kind of information flow, a relational property, which happens to be information flow. So the main idea of this monadic framework in F star is actually dead simple. It says, the way we go about it is that we already know how to add effects to F star by giving them a denotation in terms of their monadic semantics. By introducing effects into F star in this abstract way, you get a weakest precondition calculus, you can extract programs efficiently to primitive state, and so on. But when you want to reason about programs, what you do is you reason about them by revealing their monadic denotation and doing proofs about these monadic representations. And this process of revealing the underlying representation of a monadic computation, of an effectual computation, is something that we call reification, borrowing a term from Andrei Filinsky. And essentially what this means is that we reduce the problem of relating effectual programs to relating pure monadic computations. So here's the first example. So let's say I have two ML programs, stateful ML programs. And they are essentially summing integers between low and high into the reference. Okay? So sum up counts up from low to high, adding successively into R. Sum down is computing the same function but going in the opposite direction. Okay? Now, I'd like to prove that these two a relation among sum up and sum down, proving that they are equivalent. There are several ways you might try to do this. So one way, suppose you did not have a relational logic at all. One thing you could do is to write unary proofs about each of them, and prove them separately, and implementing functional correctness proof, saying that they're both implementing the same function, and then prove that the two specs that you wrote for them are equivalent. That's one way to do it. But that has some downsides in that this requires that, in order to prove this relation between the two, I needed to write the full specification of each of them separately, and then relate the specs. It's kind of through an indirection in some sense. What I would like to do instead is to say, I want to relate these two terms directly. For instance, if the only thing I wanted to prove about them is a security relation, there's no need for me to have to go and do a full specification of that, because perhaps that's not what I'm interested in. Whereas if I have to go this unary style, then I'm forced to fully specify and then relate unary specs. Besides, some kinds of properties may not actually be specified, may not actually be provable this way. So this is essentially saying that if this kind of proof strategy is going to work, then the property that you're after has to be statable as a collection of unary properties. And not every hyperproperty, a property among sets of traces, can be decomposed into a collection of properties about individual traces. So this style of doing proofs is effective at times, but not always. So what I would like to do instead is just write a relation like this that says sum up from low to high, using the same reference R, is related to sum down from low to high with the same relation, with the same reference, and the relation relates. It's a relation among commands, and it relates the monadic representation of sum up and sum down. So it relates functions from initial memories to results and final memories. Okay. So the way we're going to do this in F-star is with kind of a fight recipe in some sense. So I've already mentioned this part to you. We have a way of extending F-star with effects. We have a unary or-style program logic. You've already seen that. And now I'm going to show you what monadic reification is. I'm going to take an effectual program and turn it pure. And then we have the ambient logic, the full dependent types, to reason about pure programs. And those proofs can be automated using SMT or partial automation. Now, all of these ingredients on their own appear in many prior languages. So modeling effects using monads, that's kind of what you would do normally in many differently typed languages. Unary Horde logics and SMT-based proofs, you see them a lot in this camp. But this kind of combination of things, again, is really sort of unique to F-star. So back to our running example, we want to prove this relation. So we start by defining the state monad as the state effect as a monad. That's the state monad I showed you on my first lecture. So playing with a state monad with a get and a put. And then we're going to generate an abstract effect for it. That's our state effect. And we have our unary Horde logic that lets you take a piece of code and type it at this computation type to say that this code has state effect returning A, but requires this precondition, and it shows And to verify our programs, we can just verify them with respect to some generically good property. Like for instance, I'm only going to prove memory safety about my program. I'm not going to bother proving them function correct. For instance, sum up, the only thing I'm going to say is that I need to know that low is less than or equal to high so that I can prove the thing terminating. And I need to know that the reference that I'm working with is fine. Okay? And I'm not going to specify anything else. I'm also going to state that it keeps the reference flag. That's needed so that this thing becomes interactive. You can't get away with that. So now, there's a line of work by Andrei Filinsky called monadic reflection and monadic reification, which essentially, the way I think Filinsky conceived of it was as an implementation technique for monads, monadic programming using continuations. And there's some papers by Filinsky that show that using continuations and a bit of state, this is kind of a universal recipe for implementing monadic computations. What we're taking from this idea is that we don't necessarily want to implement monadic computations this way. We only want to reason about monadic computations this way. So we're going to say, okay, we have a way of taking an effectual computation and repeating its representation as its monadic representation, but only for specification purposes. So there's an operator that F star has called reify, that for any effectual computation, the reification of it is going to be a pure function whose type is the elaboration of this type into the underlying monadic representation. So you can see the reification of this SD computation as a heap passing function, which has to be called an initial heap H0 that satisfies the precondition and produces a result, which is a result A and a final heap that satisfies that relation. Right? So we do this only for spec. And now we can relate our two programs with the following lemma in F star. We can say, rather than the way in which I'm going to define the tilde relation is by defining it in terms of their reifications. So what I'm going to say is that this lemma saying that sum up and down are equivalent is essentially amounts to saying that, well, I need these two conditions just to ensure that the two functions that the functions are to satisfy their preconditions, that they terminate and are memory safe. And if they do, then the reification of sum up applied to the initial heap and sum down applied to the initial heap produces a pair of final heaps such that they agree on the value of that reference. So the heap hasn't changed except at suppose I should also say the heap didn't change except at that reference. And the reference, the two heaps agreed on that reference. One would add that too. Okay. Is there a question so far? Yeah.
Oh, what's reify?
Reify? Yeah. So reify is this operator. It's an operator that, given an effectual term, is going to turn it into a pure function whose type is the representation of this effectual term. There's actually sorry, go ahead.
Does reify work with whatever monadic effects you add, or only those are baked into that star?
In fact, it works only with the ones you add, not with the ones that are baked in. So, so some of the effects that are baked in may, let me put it this way. There's two kinds of reification. Okay? So this reification is a reification whose effect is ghost, meaning that this is a reification you can only use for specification. Okay? This form of reification is available for, when you define an effect in that star, you can designate it as being reifiable or not. And if you designate it as being reifiable, it comes with this operator. For some effects that are primitive, it's backing up a second. For some effects, it's safe for this representation to not be ghost, for it to actually be computationally relevant. You can reify something into its representation and treat it as if that reification were pure. And you may choose to do this for some of your effects, if that's what you want. But for some other effects, like the ones that are implemented primitively, it's never safe for it to not be closed. Because, for instance, if this really were the primitive effect of state, then essentially turning a primitively stateful computation into a state-passing computation like this requires turning the entire ML heap into a value, which you can't do. Other questions? Yeah.
What's the square brackets R on the next slide?
It's dereference of the heap at that location. There's actually a dual operator for reification called reflection. There's an operator in SR called reflect, where given a term of the representation type, you can reflect it back as an effectual term at the effective value. So it's a torsion in the opposite direction. And that too has the same restrictions in the sense, for some primitive effects, it's not safe to reflect because, again, that would require, for instance, turning the heap into a value. All right, so we can relate our programs this way. And here's how this proof actually goes. Is there another question?
Yeah, just to clarify, so reify and reflect, they're not definable in SR. You have to add them as primitives.
They are primitive, they are operators in SR.
Okay.
Primitives, yeah. Yeah, if you want more details about this, there's a paper called Dijkstra Monads for Free in Popple a couple of years ago. That is the foundation for this paper at CPP. Yeah?
What would it take to make them not be primitives? Would you need something like a logical framework?
I don't know. I think I don't see how they could not be primitive in a way because effects in F star are primitive. So you want an operator that goes between a primitive thing and functions. And so I think that would have to be primitive in some sense. I see it as just a way of controlling where you're allowed to observe the denotation of a computation. It's just sort of controlling abstraction. Right. So how do you actually do this proof? So there are many ways in which you might do this proof, and here's one way. I'm going to try to do this proof in a way that does not involve using any auxiliary specification. I want to relate sum up and sum down using only sum up and sum down. Okay? And the way I'm going to do it is by writing a ternary relation. So one thinks of often one thinks of relations among programs as being relations between pairs of programs. But to do this proof, I'm going to actually relate three programs. So the way I'm going to do it is to say, I have sum up from low to high, and that's on the left. And I'm going to relate it to sum up running from low to some midpoint, and then sum down running from some midpoint to the end on the right side. Okay, so this is a relation among one program on the left and sort of its copy on the right, and some other program on the right, the composition of two things on the right. Okay. And the proof goes by induction on this midpoint. And it requires a couple of other lemmas to get this to go through, but it does. Okay. So under the hood, the semantics of reify, reify is primitive in F star. Here's its semantics. It's essentially an operator that commutes with the monadic structure of a program. So if I have a reify of a return, and this is reification for state. For each effect, it has a suitable interpretation. So reify for return is just the return of the monad. Reify of the bind, let is just bind in F star, right? Because the let is monadic in sequence. Reify of the let is just let of the reifys. And then reify of the get is just the get, reify of the put is the put, and so on. You just push the reify inside and lift the monadic structure out. Okay. So that's the general framework. Yeah?
Is this verification safe when my effect doesn't satisfy the monad law as well?
Sorry, can you say that?
So if I define an effect
Yeah.
which doesn't satisfy the monad clause, so
Yeah.
is verification safe in that case?
No, you should have the monad clause.
Is this checked or?
No, like I said, like the philosophy in F star is that you should play by the rules, and but we're not going to insist that you do.
Okay, thank you.
And this question's come up before. I remember having a conversation with Andreas Havel. He was like, you should really check the monad laws and not allow people to define it otherwise. And, maybe he's right. So, right. So now what I'm going to do is to take. I showed you an example of this style of proof on just on these loops, but using this general setup, I can actually define a program logic for relations within F star. So I'm going to show you how to encode or sketch how to encode Nick's paper. So Nick's paper, which I have up here, is like I said, it's really nice. Essentially, he right. So let's look at this one, for instance. Basically, he's giving a set of inference rules that relate a pair of commands. And the way to read these relations are to say that if you start in a pair of states that satisfies P, and you run both commands, you end up in a pair of states that satisfies P prime. Okay, so both of these are relation. This is a relational pre and a relational post. Predicates on pairs of initial states and pairs of final states. Okay, and he gives a number of proof rules. And the proof rules are essentially, they exploit the syntactic structure of programs. So, for instance, there's going to be a rule to relate sequential, commands. There's a rule that relates skip to skip, a rule that relates sequential composition to sequential composition, and so on. So he's going to match up the syntactic structure of the program on the two sides and show proof rules for each of them. But in a way, the set of proof rules here they're incomplete, because the programs may not have the same structure on the two sides, and then if they don't, then you're sort of out of luck. So I'm going to show you how to encode that. Let's take the type of commands to be just these are true commands. They're just unit array unit statement commands. They don't return back. Okay, really imperative. Okay, so a command is one of those. And a relation between a pair of commands is defined in F star this way, that says, if I reify the first one and run it in an initial state, and I reify the second one, I get a pair of final states that whose domain is the same. They both have allocated of three the same number of references, and their values agree at every reference. The values of the final states agree at every reference. Now, for these slides, I've kind of simplified many things away. For instance, you have to show that, well, if the left side terminates, the right side terminates also, and so on. But that's in our paper and in our code, but it's not on the slide. So here's how we rewrite one of Nick's rules. So Nick has a rule for relating two assignments. And one way in which you can write this rule is to say a pair of assignments to x and y with E0 and E1 are related with relational pre and relational post if the precondition is the classic Hoare rule for assignment twice. The Hoare rule for assignment on the left and the Hoare rule for assignment on the right. Right? You guys, the Hoare rule for assignment basically says if I have a post condition and I have an assignment, the precondition for this command is just replace the occurrence of the assigned variable in the post condition with the value that you're assigning to it. Because in the continuation, the assigned value has the value of its assignee. Sorry, I don't know if that was. Should I say more? So write the whole rule for assignment. I don't know, let's see. So the classic core triple, I can just write it as a triple dummy for context. Let's see. So if I have x gets e, and I have some postcondition here, the precondition is just q with e for x, right? Okay, so that's just the same as this rule, but twice. This is the command on the left is assigning E0 to x, and it's operating on the left heap, H0. So the postcondition, to get the precondition, I'm going to substitute in the left heap the value of E0 for the heap at x. And on the right side, I'm going to do the analogous thing, but on the right side for H1. So it's the whole rule twice. To write a relation among sequential composition, it's again the whole rule for sequential composition, but twice in some sense. So if I wanted P and R are my precondition and my postcondition of the composed commands, I'm going to decompose that into saying, well, these guys are related if I can find an in-between postcondition that says that C0 is related to C1 at precondition P and postcondition Q, and C0 prime is related to C1 prime with Q and R. So it's just the sequential composition of relational triples. Now, the nice thing about setting up a relational logic in F star in this way is that I can build these kinds of syntactic proof rules to relate commands based on syntax. But ultimately, these proof rules are just theorems about the underlying denotation of programs. And if I have a proof rule, if I want to relate two programs, like sum up and sum down, that don't have the same structure, I'm not stuck, because if the syntactic proof rules don't work, I can just go and reason directly about the denotations. So for instance, in one of these syntactic systems, typically it's not possible to prove that sum up is related to sum down, because there's just no proof rules for it. The loops are going in opposite directions. They don't share structure. So I think this is a strong point of trying to embed this kind of relational reasoning into a framework that has, into any proof assistant, F star, talk, or anything, where the ultimate sort of truth is reasoning about the denotation of effectual terms as pure terms. You never get stuck in some sense. So we use this kind of thing to do other systems of this style. We show how you can get a syntactic information flow control type system in the classic style of there's a Smith and Volpeno style, the textbook information flow control, syntactic information flow control. You can derive that in F star, showing each one of those rules as a theorem about the underlying denotation of programs. And when the syntactic information flow type system is too imprecise to capture the security of your program, for instance, a classic information flow type system will, the classic thing is that if you branch in a secret, the bodies of the two branches, they can't assign to any public value, period. You must have seen this in Andrew's talk, right? So that's a syntactic approximation of information flow control. Because, for instance, if I assign the same value to the public reference in the two branches, so what? I don't lose anything. I'm not leaking anything. I'm leaking the same. I'm revealing the same information on the. It doesn't depend on the branch in some sense. And a syntactic information flow type system will not let you do this. But if you're in this setup, if I have a program that's doing something like this, I can always boil down to denotational semantics and get my proof done. We give several other examples. You want a reference to it?
Yeah.
I can dig one up and put it on my. So I should point you at this. So I'm collecting kind of lecture notes on this page off the F star dying website. I'll stick a reference to Connor's paper there. So So I wanted to show you a couple of examples of this in action. So let's see. So here is a kind of a proof of the security of the simplest cryptographic construction you can imagine. So this is one-time paths. So what's a one-time path? It's essentially saying that if I'm going to send a message to you, I'm going to sample a random key, and we're going to share the random key, and I'm going to XOR my message against the random key, and I'm going to send you the cipher, and you're going to decrypt using XOR also. Now this thing can be shown to be perfectly secure, because if I'm sampling a random key and I XOR my message against it, the resulting bits also look random, right? So so here's how you can prove that one-time pad is perfectly secure in F***. So is that big enough? One more font? Okay. So here's my implementation of one-time pad. One-time pad takes an element that is the message I want to send. Okay, and RAND is the effect of randomness in F***. So programs in RAND are going to sample from a random tape. Pull some random bytes off the tape, the tape advances. Okay, and OTP is going to do a sample, and then it's going to just XOR my message with the sample. Okay, so it's dead simple. And I want to prove that this guy is perfectly secure. So the way in which I'm going to prove it is using this lemma. And this lemma says that if I have two messages, N1 and N2, ultimately, maybe read this line first, one at the top. What I want to prove is that for all messages, all pairs of messages, N1 and N2, the probability of OTP on N1 returning some distinguished value C is equal to the probability of OTP on N2 returning that value. Okay? So, arguably, I mean, I hope you agree that this is, a statement like that is a characterization of perfect security. Right? So, the way in which you prove this, or the way you state it in F*** is to say, well, if I take OTP and I run it on N1, and I reify it, applying it to some initial tape, and I do the same on the other side, then this function, which I'm going to show you in a minute, the probability mass of F1 with respect to the point distribution at Z is equal to the measure you get on the other side for the same point distribution. Okay? And its proof is just, its proof involves essentially it involves finding a bijection among the random tapes. So you show that the proof involves saying, well, if I run my program once on the left of a particular random tape, there exists a random tape on the other side, where if I ran the program with that tape on the other side, I would have gotten the same result as running it on this side. And that the way to find the other tape is through a bijection. Okay? So all of this is kind of, you're inside dependent type theory, so you can sort of define whatever you want in some sense. So here's how we do define measures and so on. Here's the point distribution is at a particular point is essentially the distribution that assigns unit probability to that point and nothing else. Okay? And then the mass is a way to compute a measure of a function p with respect to some probabilistic computation f. And this is defined as the sum over all tapes of the function running on that tape, producing a result, and using that and computing the probability associated with that result, and summing over all. It's unnormalized, but that's the measure. Okay, and so that's one way to do probabilistic security proofs. So OTP is really simple. and not particularly realistic. Unless you share a source of randomness with your with the other party, you can't really use OTP. But here's El-Gamal encryption, which I mentioned briefly yesterday. And El-Gamal is essentially doing discrete, it's based on this diffing element assumption. It's doing exponentiation in a finite field, and it's also based on, at some level of abstraction, it looks a lot like one-time paths. El-Gamal they have two versions of El-Gamal. This is El-Gamal trying to encrypt some message M in, and M is a group element. And this is the ideal El-Gamal in some sense, and it produces just a random element in the group by not even looking at M. And this is the actual El-Gamal, which uses the message M as a multiplicative factor in the encryption. And what you can prove is that concrete El-Gamal and ideal El-Gamal have satisfy the same kind of lemma as the one I showed you for OTP. It says, if I have some message that I'm trying to encrypt, and I pick some group element C, then running concrete El-Gamal and running ideal El-Gamal produce distributions that have the same mass at C. Okay? So that's how you do these kinds of proofs. Now, I should point out that, it's cool you can do this, I think, but at the same time, it's still some ways from the kind of more sophisticated, proofs about HMAC SHA-1 and authenticated encryption and sort of building up bigger packages. Trying to scale this to that point is something we're working on. Okay, so I'm going to show you yet another way of doing relational proofs in SR, and let's do it. So So if you look at actually how cryptographers do their proofs, so there are a couple of my colleagues, Marco Holweiss and Konrad Kober. This is a slide from one of Konrad's presentations. He's a presentation he was making at a crypto conference where he's trying to show how to argue about the security of a particular construction called CryptoBox. The details of CryptoBox don't matter too much, but the way in which they do their proofs is by writing diagrams like this, where you can see each box as a functor over some functionality. So, for instance, ODH-B is a functor that relies on the key functionality and provides a functionality suitable for composition with this functionality. So each of them are functors. And they're all parameterized, for instance, by some secret bit, whether they're idealizing or not. And the way in which they do their proofs is very similar to the kind of stepwise idealization of games that I showed you yesterday, but they're doing it at the level of these functors. And the way they do their proofs is to say, okay, I'm going to consider this part of the diagram, I'm going to flip ODH-B into idealizing, turning that bit to 1. I'm going to flip this bit to 1, and then I'm going to show that the composite functionality that I'm interested in, which is this composite thing on this side, its ideal version is equal to the ideal version of all the individual functionalities split to 1. That's the level at which they'd like to operate in some sense. Okay, and that's still quite some ways from the kind of detailed code-based proofs we're doing. So how do you get from code-based proofs at this scale to allowing a cryptographer to be productive at the level at which they actually think? So one way in which one might get there is here's a direction which I think I find interesting, maybe you will too. So what I'm going to show you is how to internalize reasoning about relations and equivalences and ultimately some things called setoids inside of star. So I'm going to start with, is that big enough? The next half an hour till the end is going to be code. Okay, I'm going to step through this file. So should
Maybe a little bigger.
yeah.
That's good.
Is that good? Okay. So yeah, I have a couple of. This is also linked from the course page, so you can play with this later if you're interested. So I'm going to start by defining the type of relations. This is, see, a relation on S is just a S arrow type 0. These are going to be proof relevant relations. Okay, that's why I'm using type rather than problem. Okay, and I'm going to have I'm going to define what it means for relations to be reflexive, symmetric, and transitive in the kind of obvious way. Reflexive is x related to x, transitive is x related to y, y symmetric, and transitive is x related to y, y related to z, x related to z. Yeah.
Since we're going to step through in detail, can you explain exactly the meaning of unfold and the hash operator?
Okay, yes, great. Please ask such questions. So unfold in F star says that the type checker should eagerly unfold every occurrence of type of R to its definition. So it's
Inline?
It's like inline, although we use inline for something else actually. We use inline to mean at the time of extraction only inline this. Unfold is, as you're type checking terms and unifying them, eagerly unfold these guys. Okay. Yep.
Is there a converse mode to leave something abstract?
Yes, there is. Yes, there's. We have irreducible. And the pound A is an implicit argument. Okay, so when you write an occurrence of type off, you can omit this argument, and the type checker will be computed by unification. Yeah.
So if you don't say unfold, is that definition still transparent?
It's still transparent, but it's not eagerly unfolded. It's unfolded
When it's necessary.
when it's necessary. If it's marked unfold, it's almost like a macro. Like the type checker is going to unfold it right away.
Okay, can I understand that like the value versus all my names?
Yeah, maybe, yes, I haven't thought about it in those terms. These are pure things typically, so it doesn't matter too much. For pure computations in F star, it doesn't matter too much. Actually, someone asked me the other day about how do you control normalization with SMT? Remember? There, yes. And it's using things like this, essentially. We add attributes to terms that say, this one, you can leave, if you left it like this to the SMT solver, it would be fine, but it's an optimization to say, hey, this is just the identity function. Let's just get rid of it before the SMT solver sees it, or before the unifier sees it. Okay. Other questions about, yeah?
What exactly is the meaning or the significance of the implicit argument? Because this is clearly a relation relating A. Could I not even write it without having the pound A? Because it wouldn't know what the relation is referring to, or?
Yeah, so it's just, how should I say? So in some systems, like say in Haskell, that you implicitly generalize over lowercase variables sometimes. In F star, this is explicit. That's all. Does that answer your question?
You also had apostrophe A.
Yes.
What's the difference?
Right. Okay. Apostrophe A is if you want to write in a syntax compatible with OCaml, and you want implicit generalization of terms of type, you can write tick A. Great questions. Thank you. Yeah.
Sorry, technical question while we're flying.
terms of type, you said, is there a standard type hierarchy? I see type 0.
Yeah. So F star has a hierarchy of impredicated, of predicative universes, right? And it has it has a universe polymorphism. Okay, so a partial equivalence relation is a relation that's symmetric and transitive. I'm going to define a type of pairs. A pair on A is a relation, and here you see the use of refinements saying a relation is that satisfies is pair is a pair. And an equivalence relation is a pair that's also reflexive, and an E-rel, an equivalence relation, is a rel that's an equivalence relation. And you can, this is kind of a standard result that, you know, if you have a pair, you can turn the pair into an equivalence relation by considering its domain to be the diagonal. Right? So that's a classic thing. F star can easily prove it to say that if I have a pair on A, it's actually an equivalence relation on the restriction of A to the diagonal. Okay? And proofs like this are just, you know, SME is really good at using about this sort of stuff. You don't have to do anything. Okay. What does this one say? That actually you can look, you know, a corollary of that is that if I have two elements in A that are related by the pair, then those elements are actually also in the diagonal. Okay. So some classic stuff about pairs. So by the way, if you're some references about this. These two are pretty good, sectoids and type theory. And if you want to understand how pairs relate to information flow control, there's a nice paper by Andre Salzefeld from ESOP 99 that also about it. Okay, so now what I'm going to do is actually kind of lift pairs into the structure of types, of various type constructors. So I can take the product relation on pairs. So if I have a relation on A and a relation on B, ampersand is F star is the pair constructor F star. I can build a relation on pairs by essentially relating the components pointers. Yeah.
So when you say hash A colon type, is this universe polymorphic now?
It is. Yeah. So you tend to not, implicitly things are universe polymorphic. You can choose to make them explicitly universe polymorphic by actually binding universe variables, or by saying no, by constraining the universes to be some specific universe, like universe 0.
Just like the typical aggregation stuff in Coq.
Sorry?
So this is like kind of how Coq generalizes over.
That's right, yeah. I think Coq only recently acquired universe polymorphism, I think in maybe the last couple of years. So I'm actually not too familiar with how Coq does universe polymorphism, to be honest. So that was the relation on lifting relations into pairs. I can also lift relations into arrows, and this is now getting kind of classic kind of logical relation style of things, right? Like saying two functions from A to B are related if they take related arguments to related results. And arrow rel is a pair. That's kind of one main theorem in some sense. If I have pairs on the arguments and the results, then lifting the pair to the arrow, it produces a pair. So just to emphasize as I go along, I'm not writing any proofs, right? Like these proofs are just going, starts building verification conditions and sending it to the SMT solver. Now, this here's just a bit of notation. I'm going to say this notation hat arrow is an equivalence, a per respecting arrow in some sense. It's actually I'm defining it on any relation. So it's saying a hat arrow B is an arrow where the elements F take related arguments to related results. Okay. And you can actually show that this relation is an equivalence relation on the diagonal and so on. Okay. Now, for some really simple examples. So here's a kind of our first example. So this is kind of internalizing relational parametricity. So back to that's to your question about implicit generalization. When I write alpha, when Emacs shows a variable as alpha, in concrete syntax, actually take an Emacs or Emacs mode renders it as an alpha, and these alphas are implicitly generalized. So in this case, sorry, I shouldn't have switched between notations here. I should have probably been more consistent about the style and thing, but alpha is implicitly generalized. Okay. What this is saying is that here's my identity function. The type I can give to my identity function is that for any relation on its domain, the identity function preserves that relation. Okay? That's kind of the classic kind of relational interpretation of types that you get from Reynolds and so on. And this is internalizing that in this style. Okay? Any questions about that? Yeah?
So when we learn syntax, I have this. So what determines the arity of your operator?
Of this one?
Yeah, the operator. What determines it?
That and that. The non-implicit arguments.
Okay.
Two. Yeah. Yeah, I mean, one thing that we've been dreaming about is sort of notations and extensible syntax and allowing you to define operators with precedence and arity and so on. You don't have that. So you get these kinds of operators that are infix operators, and their arity is just determined by the number of non-implicit arguments. Okay, so that's the identity function. Now let's do some kind of security example. So I'm going to define the notion of, so you must have seen in animal this kind of labeled information flow control, where you have types. You were asking about this yesterday, I think, to a certain extent. You have like types indexed by security labels. Like this is low security, this is high security, and so on. One way to give an interpretation for this is rather than taking them as syntactic labels, to define low security as a relation. So here's low and high. So for instance, the way I see it is that a low A is an A that can be provided by the adversary. And in 2 runs of the program, the adversary has to provide the same value. So 2 A's are related by low A if they are the same. Okay? Meanwhile, high A is the secrets that are allowed to differ in the 2 runs. So the high relation on A is just a true relation. So any 2 A's are related. Okay? So you don't have to be syntactic. This is internalizing what non-interference would give you as a relation rather than just doing manipulating tags. Yeah?
So can you use this internalized relational parametricity to prove free theorems internally in F-star?
I mean, I think that's intriguing. It's and I think to do it at full generality, so here notice I'm internalizing parametricity for simple types. If you wanted to do internalizing parametricity for all of F-star's dependent types inside F-star, I'm not sure. That sounds hard. There's actually nice papers by Bernardi about these ideas, so that's some place to go look. So yeah, that's low and high. Okay. Now here's some classic information flow, tiny but classic information flow control types. So here's my function lambda x plus 45. Okay. I can give this the type low int to low int. Okay, because right, clearly the result reveals something about its argument. So it can only handle public values, returning a public value. Here's, but the same function can also be given the type high int to high int. It can manipulate secrets as long as the result isn't also given to the adversary. It can also be given the type low int to high int. It manipulates this is the easy case. I got a public value from the adversary and I'm going to not give it back to him. So that's easy. But if I try to give it this type high int to low int, that's saying I took a secret and I gave it back to the adversary. That fails. And that's an abstract pragma that says the next definition should fail with error 19. That's our type checking error. So if I take this out and try to type check it, abstract is going to say, it says at setoids.150 whatever that source location was, the assertion failed there. Okay. And I have some debugging to turn on. So it tells you, oh, I asked the SFT solver 4 times with different configurations, and it kept saying no. Okay. But here's a function from high to low. It takes a secret, and you can give it back to the adversary because what it returns is a constant. Right? So that can be given type high to low. And notice that this is the same function, as you may have seen already. The same function can be given many types because terms may satisfy many relations. And this, in some sense, is the raw type. Lambda x, x minus x, the most kind of primitive type you can give it in a start is int arrow int. But it has all these other refinement types too. Like, well, this one, x plus 45 also has type int arrow int, but it has all these other types as well, with many others as well. This assertion here, so assert is a way in abstract to say, hey, check this. I'm asserting a property, check it. Try to prove it. Okay? So what I wanted to emphasize here is that when I write a type like this, I'm essentially proving a relation between a function of type int arrow int and itself. But nothing prevents me from doing more interesting things. So this assertion is saying f 5 primes, right, is related to itself at some other type. Even though it was given this type later, I can say, hey, assert that it has some other type too. Okay. So now I want to say, okay, that I can do more complex things, functions that manipulate secrets and public values. So here's G. G takes one intuition that you should keep in mind when reading these types is that wherever normally you might write a type, you instead write a relation. Okay? That's the classic kind of Reynolds thing, right? Like every type has a relational interpretation. So we'll just write relations wherever we expect types. So if you look at G, it's just an int cross int arrow int cross int. But I'm going to give it wherever instead of writing types, I'm going to write relations. So it's instead low int cross high int arrow low int cross high int, and the arrow is relational. Right? So what this is saying is that it's a function that manipulates, has one public value, one secret value. It returns a public value and a secret value. And the public value that it returns is actually manipulating the secrets, but because this is semantic, it doesn't matter. If you were doing this syntactically, typically you'd say, oh, this operation, it's manipulating secrets, the result must be secret. But it's manipulating secrets in a way that doesn't depend on the secret. So it's fine. Okay, so you can do other examples like this. And here you can also say, here's another bit of starism. We have squash T means this is a, it's a proof irrelevant proof of T. Okay? It's a proof irrelevant statement about T. So the inhabitants of squash T are just units. But they're units in a context which satisfies the property. Okay? So here, what I'm doing is that I have G and G prime, both of which have some relational type. Say this is saying G double prime is related to itself at that type. But now I can prove that G is related to G prime at some other relation. I'm going to go a bit more quickly. So play with this if you're interested. So I'm going to now kind of start going kind of up the stack. So let's say I want to do a state monad. I can do a relational state monad where the state monad is typically S arrow A cross S. But remember, wherever I write types, I'm going to write relations instead. So the state monad is now a relation on S's to a relation on A cross S. And it's a relational arrow. Okay? And the relation on the state monad is just the arrow relation on its arguments and its results. And I can define bind and return and everything relationally. So here's bind. Its implementation is the classic bind for a state monad, but its type says that, hey, if I have a, here's another F star, so you're going to wonder what the dollar is over here. And the dollar is a unification hint. It says when you're applying bind, F star has subtyping. So subtyping and unification typically are tricky to make to work well together. And when you annotate an argument of a function as dollar, it says at an application site for this function, do not use subtyping for this argument, just use unification. Okay, that's a unification. So bind, it's like I said, it's classic implementation of bind, but its type is telling me that if I have a relational state monad computation F, and I'm going to have a relational continuation for that computation, and the whole thing is still relational. It respects the equivalence relation on the state monad. Return is the same. All the actions they have their classic types, the implementations, but they now have relational types. And now I can instantiate my state monad to some specific state. Let's say I'm going to pick my state to be low int cross high. So my state contains a public component and a secret component. And I can define operations to derived operations to get each component of the state. And I can do here's a couple of ST types. Here, say, this is just a type. T1 is the type of functions from low security integers, stateful computations that are returning low security integers. And this one is similar, but it's returning Boolean. And I can write classic state, monadic computations. This, by the way, is F star's. F star has a kind of a simple do notation, where notice I did not define any effect here. I'm just working with monadic representations. If you're working with these monadic representations, then you don't need to use this kind of do notation. And I can implement several kind of classic, very simple programs that have these relations, and I can relate stateful computations. Saying, for instance, that I don't know. Here's a trivial example. I have 1A and 1B. Both have type T1, meaning they take low integers to low integers, and they're syntactically different. They're doing an addition that in different numbers, for instance. These are trivial equivalences, but I can prove that 1A and 1B are related to themselves, and that they're related to each other. Okay, so that's concentrations. I'm trying to, now I want to get up the stack to deal with the stuff that Markov and Conrad want, which is they want to reason about modules and functors and equivalences among them. And so I'm going to sort of try to pull myself up by the bootstraps, get up to do relations on modules and functors by encoding them. So I'm going to encode modules as dependent maps. So but in 2 steps. So first, modules have signatures. The signature of a module is, you can think of it as I see a module that kind of like a record, right? It's got a bunch of labels for each of its fields, and each of its fields has a different type. Okay? So a signature of a module is a map from labels, some type of labels that I'm going to pick. It could be like string, at, or something. And for each operation in the module, it's indexed by a label. Each operation has a type. And associated with each of those types, I'm going to have a partial equivalence relation. That's again with my sort of relational hat on. Every time I have a type, I need to attach a relation onto it. So here's the per associated with each operation in the module. And a module is just a module is indexed by its signature, and it's a dependent map. So what's a dependent map? You can see dependent map is just a dependent function. It's a function whose codomain has a type that depends on its domain, and it's like a heterogeneous function. Yeah.
So what's the no EQ about types?
So by default, when you define a type in F star will try to prove that type has decidable equality. To disable it, you can say, hey, I know that this type so clearly doesn't. It's got functions between at type level and so on. Don't try to derive equality for it with no equality. Yeah.
So ops defines the methods and like the values, right? For a signature, how do you define like a type?
Ops is are the types.
Oh.
So this is saying the signature says. So I'm going to give you an example. This will be a little less abstract of an example. Hold on a second. I think you'll see it. So let's look at this example. Give you a second for your example. Okay, here's an example. That's a signature. The labels are drawn from this type of keys. This is a module that has 2 operations, 1 and 2. Okay, it has and the operations have types, where the type of the operation 1 is T1, the type of the operation 2 is T2. That's what this ops is. And then the associated with each operation is a relation on those operations, and operation 1 has that relation and so on. So the signature is just the specification, just the types. And the values are going to be these maps. Okay, given a pair of modules that have the same signature, I can define a relation on modules by saying that each operation is related pointwise by the relation associated with that type. Okay, and I can also prove that since pointwise every relation is a per, this pointwise computation is also a per, but now at the level of modules. And I can give some, here's some simple examples. Here's a trivial module. This is the unit module that has one operation, and that operation has type. Okay? And here's how you create an instance of that type. It has one operation type. Okay? Here's some silly modules. This is the empty module, the module that has no operations. Its key is false, right? And here are sort of some other modules with instances of that. And finally, functors are functions from modules to modules, and they too can be given relational interpretations. Where I see a functor as taking a functor is indexed by 2 signatures: the type of the module that it consumes and the type of the module that it provides. And this thing is a relational arrow manipulating signature relations on the, I call that the underlay to relations on the overlay. And you can build functor composition and prove functor composition associative while preserving relations and so on. And you can even define things like functor instances. For instance, here's by doing all of this inside the logic at the term level, I can define functors that you typically wouldn't define in a module system. Because, for instance, here's the polymorphic identity functor that quantifies over all signatures that you couldn't write in a model, for instance. Because the module system is at different levels. Anyway, so I think I'm close to running out of time. What I want you to take away from this is that you can do this kind of internalization of relational reasoning inside F star in several ways. I showed you one way to do it from the CPP paper that was about how you do things with monadic reification. And I showed you another way of doing it, which is kind of internalizing relational parametricity into the types. And I think both of these are kind of, I think they're selected cute. I don't know how to make it work at the level of huge programs. And I think that's kind of end of the research agenda. How do you get this kind of stuff to work at scale? Yeah.
Can you elaborate on somewhat more on how they relate and what is currently prohibitive to scale them? I have got some kind of intuition from what you presented. Maybe you can comment more. Not how to solve the problem, but
yeah.
What is the problem?
I think part of the problem is, if I had I'm working with a very rich memory model with things like private state and sort of the C-like memory model with lots of data structures and arrays and stuff in memory, pointers. What is a suitable relation, to work with things like this? Here, in this very simple memory model with just integers and booleans, it's a very natural. I can easily define low security, high security, and so on with these structures. But if I have a much more elaborate effect, what is a suitable logical relation to work with those things? That's one difficulty. Yes.
I was wondering why you get away with the CPP approach, because intuitively, because you're basically taking the identity in that and saying that's the relation I have on my memory.
Yeah. There too, I think we get away with it because we define these kind of very precise relations there and work with it. But essentially, what I think the limitation of that is that essentially doing a detailed proof amounts to then just working with the broad denotation of programs. And at scale, this is saying, wow, I have a huge function that has, it's represented by this pure function in F star, that's fine. How do I prove a relation among them? My head explodes. The proof, my goal looks like, 100 pages of text, like relating two things. So, you need more structure somehow to rate that in control. So I think maybe the answer lies somewhere in perhaps something like what Nick Benton was doing. Maybe we could have a set of syntactic proof rules that allow us to do syntactic proofs on large terms as much as we can by relating their structure, and falling down into reasoning about denotations only in the most subtle places. And maybe that could be automated by a tactic or something. Yeah. Still, I think it's, if you leave aside trying to do proofs about implementations for a moment, I think it's fun to play with internalizing parametricity. Doing a bit of semantics in this style, I think is also fun. So maybe some of you would be interested in playing with that. So, any other questions? Yeah.
You mentioned that there's a limitation in the freedom of expressing user-defined syntax. Right?
Yes.
In, let's say, comparison to Lee.
That's right. Yeah.
Would you, if I had an application where that would be important, would you recommend splitting the proof work between the two systems, or should I just wait a year until you have built in how we approach that.
Yeah, I'm not sure you should wait. We've been talking about this for a while, and it's changing the front end of your language is stop for a while, stop doing everything, change the front end, port everything, and it's a big, there's some engineering overhead to it. So I hope it'll happen sometime, but at the moment, other questions? Okay, thanks.